We have defined last time limit superior and limit inferior of sequence. Now we shall see the relation between limit superior and limit of a sequence. If a sequence is convergent, then these two are the same. Limit superior of Sn will be same as limit of Sn. That is our first result as theorem. If Sn is a convergent sequence, if Sn is a convergent sequence, then limit superior of Sn is equal to limit of Sn. See, we may see that limit superior, limit inferior and limit. So these three concepts are there. So it is similar to left hand limit, right hand limit and limit. When we say limit of a function exists, if left hand limit is equal to the right hand limit is equal to, and that is equal to the limit of the sequence. And here for convergent sequence, limit superior is same as limit of sequence. Example of convergent sequence, we know 1 by n is a convergent sequence and this sequence tends to 0. So therefore for this sequence limit superior is same as limit of the sequence, because if you consider limit superior, we have to consider mn as LUB of Sn means 1 by n, 1 upon n plus 1, Sn plus 1, Sn plus 2, etc. And what is the least upper bound of this set? Maximum element or the greatest element of this set, that is 1 by n. And limit of mn, that is 1 by n, is same as limit of the sequence, which is also 1 by n, and both tend to 0. So limit mn is the limit superior and both will be the same. So here we shall suppose first limit of Sn is equal to L. In the proof, let L is equal to limit Sn, limit of the sequence as n tends to infinity. And we now apply the definition of limit of a sequence. For given epsilon greater than 0, there exists n belongs to I such that mod of Sn minus L is less than epsilon for n greater than or equal to n. And now what this will imply is L minus epsilon is less than Sn is less than L plus epsilon, meaning of absolute value. This value lies between minus epsilon and plus epsilon. We have added L throughout, and this is true for n greater than or equal to n. Now that means every value of Sn when n is greater than capital N, that Sn lies between L minus epsilon and L plus epsilon. So therefore L plus epsilon is an upper bound and this is not an upper bound for Sn. So if you consider, that means take the LUB of Sn. So therefore L minus epsilon is less than least upper bound of Sn plus 1, Sn plus 2 is less than L plus epsilon. So LUB of this set will lie between these limits L minus epsilon and L plus epsilon. And now we can consider the LUB limit of this LUB, and then the limit will be between L minus epsilon to L plus epsilon. Taking limit as n tends to infinity, this will give L minus epsilon is less than or equal to limit. When we take the limit, the inequality becomes weak, that is strictly less than becomes less than or equal to LUB of Sn plus 1 etc., and is less than or equal to L plus epsilon. And what is the limit of LUB? That is limit superior. And thus, by definition, it is Mn. LUB of Sn etc. is Mn, and limit of Mn is the limit superior. Or this implies L minus epsilon is less than or equal to limit superior of Sn as n tends to infinity is less than or equal to L plus epsilon. And this is true for n greater than or equal to L. So we have this is true for n greater than or equal to capital N. And further, what this will show is that limit superior lies between L minus epsilon and L plus epsilon. Epsilon is arbitrary. That means that it can be taken as small as we want, and therefore this is between L minus a small number and L plus a small number, means it will approach towards L when epsilon is very very small. But we can write epsilon is arbitrary. And therefore this shows that this implies limit superior of Sn is equal to L. And thus finally we got limit of Sn is L and limit superior of Sn is also equal to L. So this proves the theorem. And now we shall consider the converse of this theorem. What the converse says, as so this same result will be true for limit inferior of Sn. Limit inferior of Sn, if Sn is convergent, then limit inferior of Sn is same as limit of Sn. So that is the next theorem, and you should try for the proof of this theorem. If Sn is convergent, then limit inferior of Sn is equal to limit of Sn as n tends to infinity. What is the difference? Superior is replaced here by inferior. And to prove this, we should consider the same step here. And instead of LUB, what we have considered is GLB. GLB of Sn plus etc. And that GLB will lie between this, and take the limit of that GLB of Sn plus 1 etc. It will be limit inferior, and that is equal to limit of the sequence. So for convergent sequences, limit superior and limit inferior is same as the limit of the sequence. These are not different. Now the converse of this theorem. If Sn is a sequence of real numbers, and if limit inferior is equal to limit superior, then that is the limit of the sequence. And if limit superior of Sn is equal to limit inferior of Sn is equal to L, then limit of Sn is equal to L. So for convergent sequences, all the three are same. Limit of sequence is same as limit superior of the sequence is same as limit inferior of the sequence. So this is the converse of the earlier theorems. What earlier we have proved, if limit superior is equal to limit of the sequence and limit inferior for convergent sequences, then the sequence is convergent here. If the two limits are equal, the sequence also converges to L. So that we have to prove. Now the proof of this theorem. We shall first consider limit superior is equal to L. So it is given L is equal to limit superior of Sn as n tends to infinity, and this means limit n tends to infinity of LUB of Sn plus 1, Sn plus 2, etc. So this is L, and from this, so what we can say is the least upper bound of this sequence is equal to L, and the least upper bound will approach towards L. So this we have to consider. So we shall apply the definition of limit of sequence. Limit of this sequence is equal to L, and that means absolute difference of this and L is less than epsilon. So given epsilon greater than 0, there exists we say N1 belongs to I such that absolute difference of LUB Sn plus 1, Sn plus 2, etc. minus L is less than epsilon for n greater than or equal to n. And what this further implies, this value lies between L minus epsilon and L plus epsilon, or this expression lies between minus epsilon and plus epsilon, we add L. So this implies L minus epsilon is less than LUB of Sn plus 1, etc. is less than L plus epsilon. N is greater than or equal to N. Now what this further implies is Sn least upper bound. Least upper bound means the greatest value or the maximum element of this set is less than L plus epsilon. We consider this half part, and therefore every term of this sequence is less than L plus epsilon. For example, if you consider the set as earlier, say 2, 4, 6, 8, 10. What is the LUB of this? LUB of this least upper bound of this is 10, maximum element, and LUB will lie. So between 10 is the element, so this we can consider 11, between 11 and 9. So least upper bound of this set lie between 9 and 11, which is 10, and therefore we can say every element of this set is less than L plus epsilon, that is 11. Every element of this set is less than 11, and thus we can write Sn. So this implies Sn is less than L plus epsilon or n greater than or equal to n. One part we have obtained. As considering this part, every element is less than this element. So which is L plus epsilon here. Now we consider the another part. Now we shall take the second half part of this. First we have considered limit superior is L. Now we shall consider L is equal to limit inferior, and we may assume this as our first result. Similarly, L is equal to limit inferior of Sn, and that is limit n tends to infinity. By definition of limit inferior is limit n tends to infinity of GLB of the set. Sn plus 1, etc. And again we apply the same definition of limit with the same procedure will be there. So given epsilon greater than 0 or there exists, we keep the same epsilon. Here we have taken epsilon earlier, we keep the same epsilon and only we change n2. Therefore there exists n2 belongs to I such that the absolute difference of this and L, that is GLB of Sn etc. minus L is less than epsilon, and this is true for n greater than or equal to n2. Or further, as like this, this value lies between L minus epsilon and L plus epsilon. Or therefore L minus epsilon is less than GLB of this set is less than L plus epsilon, n greater than or equal to n. Now what we have to consider is the left half part of this. Earlier we have considered every Sn is less than L plus epsilon. What this says that minimum element of this or least element of this is L minus epsilon is less than the least element of this, and therefore L minus epsilon is less than every element of this. Or what is the GLB of this set? Say 2, 4, 6, 8, 10. GLB is this 2. And if an element is less than 2, then it is less than every element of this set. And therefore this left half part is true for this. Or that implies L minus epsilon is less than Sn. Every member of this set. And this is true for n greater than or equal to n. Now we shall consider this as second statement. So this implies, now we consider n maximum between n1 and n2. Then both 1 and 2 will hold. So for this purpose let n be maximum of n1 n2. Then from 1 and 2 we combine 1 and 2. See, what we have is L minus epsilon is less than Sn, and one is Sn less than L plus epsilon. And this is true for n greater than or equal to capital N, because we have selected capital N as maximum of n1 and n. So both statements will hold for this maximum value. And what this shows? This shows that Sn minus L is less than epsilon for n greater than or equal to n. Or this means limit of Sn is equal to L. Or this proves limit n tends to infinity of Sn is equal to L. Or thus, if limit this proves the theorem. Limit superior and limit inferior are equal, then that is the limit of the sequence. So if these two are equal to L, then that is the limit of the sequence. So thus for convergent sequences, these all are same. Limit inferior, limit superior, limit are the same. And converse also true. If the two are equal, limit superior and limit inferior are equal, then limit of the sequence is also equal to that value. So this completes the proof of the theorem. So remaining result we shall consider next time. Thank you.